Hi, Kristen. How are you?
Hi, John. How are you?
I'm good. I'm good. Glad you were able to give a talk today. It's going to be fun.
The commute was tough, but you know.
Yep. And you're going to have all these complete strangers to talk to.
That's good.
Oh, well.
Hi.
Hello.
Good to see
How are you, Sarah?
Good. It's good to see you.
It's good to see you too.
It's been so long.
Yeah. How are things with your little one?
Good. Actually, I just passed her off to the husband and she's good. Good. She's going down for a nap. Perfect time for this talk. So I'm very excited. Good though.
Fantastic.
Hi, Dana. How are you?
Oh, hello,
Good
Pep.
to see you.
How are you?
Good to see you.
Oh, it's so good to see
Forward to
you
your
too.
talk. Thomas, hi. Hello. Good to see you.
Hi, Thomas.
Everyone.
Yeah, Zoom is not as good as in person, but you know what? I'm glad we have it. It's better than nothing.
Absolutely.
It's true.
It's better only in one sense. Most everybody is on time.
Isn't, you know, that's very interesting. I've noticed that I struggle with being on time, and people are on time for Zoom calls. 5 minutes late doesn't cut it.
Yeah, and if you're like a minute or two early, it's that kind of awkward silence. But I find more people are early for meetings these days too.
Okay, so you let me know when I should.
Sure. I'm going to give it another minute or two since I expect a few more than 23 participants, but not too long.
Okay.
And I'll say a couple words of introduction and we'll let you go right into it.
Excellent.
I'll be right back.
Oh, this is an interesting question. Kristen, the session's being recorded. Is that okay with you?
Yes.
Okay.
Yes, my Joanne had asked me for permission before.
Oh, good.
So you're all set.
Yeah, and we have a YouTube channel too where we put all these talks, and it I think actually people watch them after, so they're really helpful resource for people down the line.
Excellent.
Okay. Well, we may actually be leveling off on our participant list, so I'll just go ahead and start my introduction. So I'm delighted to introduce our own Kristen Dana. She's a professor in electrical and computer engineering here at Rutgers. She's a member of the executive council at RuCCS. And I'm really happy to have her speak to the RuCCS community today. I know not everybody knows her or knows her well, and I'm delighted to provide this opportunity and to take advantage of this opportunity. Kristen got her bachelor's in electrical engineering and computer science from Cooper Union and NYU. She went to MIT for a master's in engineering and eventually earned her PhD in electrical engineering from Columbia. She's been a very accomplished scholar. And she's well known for her work in computer vision, including computational models for recognizing the textures of objects within images, and a diverse set of applications of those technologies in the real world. But today she's going to talk about something else entirely, which is the emerging applications of robotics and their impact on society. The title of her talk is Socially Cognizant Robotics. I'm looking forward to it.
Thank you for that introduction. You know, it's funny, I've been a computer vision scientist for most of my professional life, but I started with an interest in robotics. But in the late 80s, robotics, well, we were coming upon the AI winter, and it was very difficult to proceed in robotics. So myself and many other want-to-be roboticists moved to computer vision. And now I see the trend many, many years later of computer vision scientists revisiting classic robotics. Well, modern robotics, I should say. Okay, so let me share my screen. Oops. So the way I have divided this talk is, first I'm going to talk about our new NRT, because I'm very excited about it, and I want to get the word out to as many Rutgers folks as I can, because it's it's the kind of program that we hope to have many participants beyond the core faculty. And then I'll talk a little bit about robot navigation and some of the recent works in robot navigation, and sort of as a case study for what unites the computational side and the human navigation side, and some papers that have interesting common threads. And then I'll talk about some recent research from my lab, from one of my recent papers with my graduate student, Faith Johnson. And hopefully we'll have time for discussion too. All right, so the name of the NRT is Socially Cognizant Robotics for a Technology Enhanced Society. So what is this NSF-NRT? It's kind of the outgrowth of what used to be IGERT. And as many of you know, Rutgers had a very prestigious IGERT in perceptual science. And their IGERT is no more, but the NSF-NRT, National Research Traineeship, is similar. So it creates this bold, new, transformative model for graduate STEM education. And nationally, there are only about 14 or 15 awarded, and each institution gets $3 million of funding for 5 years. And almost all of that funding goes to trainee fellowships. It's a unique grant in that sense, because it really, the focus is on supporting fellows. And each university can only submit 2 proposals, and we were awarded our NRT this September 1st, 2020. So it's really just getting started. So what is this idea between socially cognizant robotics for a technology enhanced society? So when you think about the socially cognizant part, you think about human robot interaction, right? So individual interaction through speech and vision and action. And so the fields that are encompassed are traditional robotics and language processing and computer vision. And then the other side of the coin is the technology enhanced society. What is the societal impact? At some level, robotics should be improving the quality of life for people in society. So how is that done? So we need to consider robotics with human in the loop. There's just kind of an HCI, HRI kind of thing, but more than that, but to include society as well. And the interesting thing is to frame these quantitatively. Right? We all have an intuitive sense of whether something is good or not, but how do you change the metrics of performance to account for the individual's well-being and society well-being? We think about metrics of performance traditionally in robotics as speed, efficiency, cost savings, and there are metrics that can be used on the human side and the societal side, but one has to do it in an interdisciplinary manner. Right? The engineers in the room and the computer scientists don't necessarily use those kind of metrics. So the key questions are what research can catalyze a positive social impact with feasible advances in the state of the art. So the word feasible is actually a little bit loaded there. And this is why the STEM side needs to work with the social science side, because one can hypothesize, oh, there will be human-like robots that can do everything a human can. But frankly, that's not going to happen in the near term. So what's, I think, one of the interesting trends in our program is to concentrate on what's feasible with technology, but still make meaningful impact. And how can costly mistakes be avoided in robotics technology development and adaptation? Right, so we know that sometimes technology is either, let's consider the issue of trust. Sometimes technology is either trusted too much or trust it not enough. You might have, a good example might be in automated driving, where you can trust too much by taking your hands off the wheel and taking a nap when you put on your automated driving at this point in the game. The technology is really not there to do that. Or it can be the opposite, where you simply don't want this automation to happen because you have a distrust of it. So this can be studied in a disciplined way. Our goal is to have incoming cohorts on two sides. One is the social science side, cognitive science, psychology, planning, and public policy, the Blaustein School. And the other is technology, electrical and mechanical engineering, and computer science. And in fact, that description represents 5 different departments in Rutgers. And then the program kind of merge socially aware technologists and technology aware social scientists. And our outcome, our planned outcome, is socially cognizant roboticists. Okay, so and the 5 departments that are involved are ECE, computer science, mechanical engineering, planning and public policy, the Blaustein School, psychology, and of course, cognitive science. Now, there are 7 underlying disciplines, right? So the 7 underlying disciplines are best seen in this figure. Robotic embodiment, control algorithms. This is the domain of both, there's blurry lines in mechanical engineering, electrical engineering, and computer science, but these are all very much on the STEM side. Visual learning, computer vision, and human vision, language and dialogue. And as we move down this path, you see that these 7 disciplines become more on the behavioral and social sciences side, cognitive modeling, behavioral research, planning, and policy. The training program that is Socrates will have both master's and PhD students. We're introducing 3 new courses. One is the Socially Cognizant Robotics course, which we've already introduced and is a course having its inaugural semester this spring 2021. We will, right now it lives in the ECE department, but we're going to be cross-listing it to the 5 departments. And all students are welcome to take it at any point, but there's an advantage to cross-listing it so that they don't have to worry whether it counts for their electives. The second course is Robotics and Society. And this course will talk more about the planning and public policy side. There's a lot of policy, legal issues that are just arising due to automation. Pulling from that example of automated driving, one policy issue or a legal issue is who is responsible when something goes wrong. Is it the owner of the car? If the owner of the car wasn't driving or wasn't responsible for the driving, is it the engineer designing the algorithm? Is it the owner of the company? Right? These issues which didn't exist before do exist in the upcoming robotics, integrated robotics world. Then the third course, there will be electives. Each of the students will take their typical electives from their home department. The third course will be a Socrates design course. And for master's students, this can also be their MS thesis. But for PhD students, we see this as the kickoff into their PhD research. After a year or 2 of courses and the first 2 courses in robotics, a little bit more technical, and Robotics and Society, both sides, both incoming cohorts from the social science side and from the STEM side, will be better prepared to do research in an integrated field. And this Socrates design course will be the springboard for their PhD thesis. The next thing that we've proposed to build, and I see this figure as interesting because we're not really on campus very much, but a test bed that can be used with various research projects and the Socrates design course. And we're going to call it the Rutgers Robotics Live Lab. And the idea is that instead of a robotics lab that sits in a lab and has tasks that aren't really very realistic, aren't real world, but rather contrived tasks confined to a lab, what we want to do is have a series of heterogeneous robots that can actually go out and about on campus and do real tasks for campus society. And the framework here is to use campus as a model of society. Right, it is a community. It's a community within our society, but it lends itself fairly well to being a controlled environment that is in between the confines of a lab and the general society. And you can see some of the things that the students will be working on: socially aware robot embodiment, data-driven control for interaction with people, human-guided vision-based robot skill acquisition, behavior-based multimodal human-robot dialogue, and other nice topics for a Socrates program PhDs. I guess actually, if I put it in slideshow mode, you can probably see it more zoomed on your screen. So let me do that. Okay, so let me talk a little bit about this first course, the socially cognizant robotics. It's going, so we are already teaching it. I've taught 3 lectures so far. Today, Jacob Feldman is teaching. And the course is intended to provide students from interdisciplinary departments with this subset of technical skills in robotics. We're using a robot simulator. This semester, we're using Copilia Sim. If anybody has their favorite robotic simulator that they'd like to suggest, we're open to suggestions. But so far, this one is working out reasonably well. And key to bringing the students who are technically oriented, but more on the social science side, onto the same STEM level as the STEM students, or a similar level, is the utilization of open source software libraries. So a lot of computer vision, robotics, and deep learning have been somewhat commoditized in open source software libraries. So with the proper tutorials and a little bit of a learning curve, one can put together systems in computer vision and deep learning without too much. It's not hundreds and hundreds of lines of code to put together basic systems. And recent innovations at the intersection of deep reinforcement learning and human behavior modeling is something that we're very excited about. So these are the specific learning goals. I don't want to go, I'm going to pick and choose which topics to go into so that we have time for everything a little bit more at the end. And here's some of the socially cognizant topics. One of the things I'd like to draw your attention to is these 4 application domains. So as part of this program, what we've done is narrow in on specific application domains, because robotics can really mean anything, right? We in a brainstorming, when we first put together the proposal, the ideas were really very, very broad. So we decided to focus it a little bit. And we have these 4 application domains that we intend to pursue in the classwork and the research projects within the program. So the first is mobility and strength assistance. The second is food preparation. The third is trash and recycling pickup. And the fourth is smart buildings. So by robots, we don't really necessarily mean the classic image of a robot that you have in your head as a humanoid or even some sort of mobile device, but even a smart building is a robot. So with the reason for these 4 application domains is we can do some simple experiments in a campus setting. the challenge is for robotics for everyday augmented living. And so the thought is that in order to use robots to improve the quality of life, one needs to think about what is the everyday tasks, both in life and work. And these application domains give us a nice set the stage for some experiments. Okay, so we also talked about navigation as an interdisciplinary case study. This was one of the lectures, and I'm going to talk about some of the papers that we discussed in this week too. This is the software tools. And then the students will learn intro to cognitive science, decision-making by human agents. How can cognitive science improve robot simulators, for instance? One of the issues that that my student and I are faced with as we're putting together some experiments with robot simulators is we'd really like to have humans simulated in the environment as well, because we're trying to build socially cognizant navigation robots. But in order to make realistic human simulations, you certainly need to know a lot more than you would if it's only a robot simulator. So how can robotics be incorporated in behavioral studies in real world scenarios is kind of flipping the coin. How can studies of humans help the robot simulators, but on the flip side, how can robotics be incorporated in behavioral studies? Okay, robot vision is another component of the course, 3D reconstruction, recognition, semantic segmentation, and then human-guided vision-based robot skill acquisition is something we're really excited about. Learn by example paradigms, where you learn visuomotor control. This is an area of robotics that really will change the way we interact with robots, when robots can watch us and learn by our example of how to do things without the human needing to do any programming. And it's something that it's a theme that we've seen, but there's still a lot of work to do, a lot of open issues. It's not a solved problem. And then the students will learn robot planning and control, navigations, kinematics, grasp, motion planning, robot embodiment, grippers, manipulators, soft robotics, exoskeletons, language processing, information retrieval dialogue versus collaboration through language, and research on how to use contextual knowledge and behavioral models about users' goals or interaction. Week 11, human interpretation of intentional behavior, aka mind reading, the intentional stance, biological motion, theory of mind. How can human style intention interpretation be incorporated into robot design? So we have a very ambitious syllabus for this course, and the core faculty are all pitching in to put it together, and I think the students will have an amazing breadth of information at the end. The final weeks will be frameworks for social science, collective decision making. These last week 12 and 13 will be taught by professors from the Blaustein School, Clint Andrews and Hal Salzman. And social science research methods for robotics, quantifying how robotics and society interact, ethnographic observations, sensing technology, survey research, and experiments. And this is what I was getting at where, this is what I was getting at earlier when I said it's not enough to qualitatively talk about robots being good for society, but rather it's an important component of the program will be giving the students the tools to quantify using social science research methods. So Socrates will have an industry consortium. We have some companies that have agreed to be part of this consortium. If anybody has additional companies who would like to be part of this industry consortium, just let me know. This is the Socrates core faculty and students. So myself, Kostas Bekris, Jacob Feldman, Jingyang Yi, Clint Andrews, Pernilla Hemmer, Dan, Faith, Matt, Hal, Aaron, and Kathy. Okay, robot navigation as a case study. In this part of the talk, I'm going to discuss a couple of papers in related work to set the stage for why some topics can be looked at in two different fields, one the computational side and one the human side, and robot navigation is a good example of that. And then after we discuss some of the recent work in the literature, I'll tell you about a specific work going on in my lab and some of the directions that we hope to go in. All right, so in this related work, I have about 3 or 4 papers that I'm going to discuss. I want you to think about some trends. One is, notice the issue of whether humans use maps and whether machines should use maps are present in both of the papers, and they're analogous. Notice the graph representation posed in the psychology literature is similar to that used in the computer vision paper. And I apologize to early on to my psychology colleagues. I will present some of this work with my electrical engineering knowledge, so you can feel free to correct me. And then notice that the issues of learning, so for instance, curriculum learning that are relevant to humans are also relevant to machines. Okay, so the first paper is by Gupta et al. in CVPR 2017, Cognitive Mapping and Planning for Visual Navigation. So the idea here, the goal is you have a robot equipped with a first-person camera, and it's dropped into a novel environment that it hasn't seen before, and it has a goal, and it needs to navigate the environment. Now, this paper starts off citing a classic paper, Cognitive Maps in Rats and Men. And I guess the idea behind this paper, from what I understand, it's a classic paper, is the argument that in navigation we have a cognitive map. Humans have a cognitive map, and they use it for navigation. So the reason why the CVPR folks, Gupta et al. were looking at this is because they wanted to contrast it with what was the state of the art, especially at the time, just a few short years ago, in computer vision and robotics. The idea, the classic way to do things was to build a very precise map of the world. Not a map that would be just enough to navigate, but go in and explore the environment. And
they just showed her getting shot. Please don't care.
So I'm going to ask everybody to mute. Thanks. Oh yeah, so the classic approach is overcomplete. You go in with a robot or a LiDAR device and you map everything, and you have this full 3D map of the world. This is a top level view of the map, where all your walls are and things that you can't walk through, and you have it in some Euclidean space, and then you path plan. Then you run the algorithms for path planning to find the shortest distance. The idea is that classic approach is precise reconstruction of everything isn't necessary. Also, it's incomplete. It was only geometry, no semantics. And there was this separation between mapping and planning. Now, the modern approaches, interestingly, ignore the structure of the problem. So from pixels to action is a very important theme in modern methods of computational navigation for automated systems. As I go and describe these papers, you'll see this from pixels to action theme happen again and again. In this paper, there's two key ideas: a unified joint architecture for mapping and planning, so that mapping is driven by the needs of the planner, and then a spatial memory with the ability to plan given an incomplete set of observations about the world. So let's see, do I have a? That's another. I don't have their architecture. But as humans, when we navigate through the environment, our previous experience help us. And I like this analogy. Humans can often guess, for example, where they will find a chair, or that a hallway will probably lead to another hallway, or perhaps at the end of the hallway will be the bathroom door. There's some semantics. It's not just geometry in our map. We have this map with some geometry and some semantics and some prior experience. So in classic, the classic way to do things was to separate mapping and planning, create the map and then do the plan. But this separation, the authors argue that the separation between mapping and planning makes the overall system unnecessarily fragile. And I really like these two examples. They're very relevant. The mapper might fail on textureless regions in a corridor. And if you're doing 3D reconstruction, you need visual features to be able to do the stereo, for instance. And if you are looking at a blank wall, there's no texture, there's no way to create the 3D reconstruction, so the whole system can fail. But precise geometry might not even be necessary if the robot knows that it's just a hallway, and chances are you just go straight, and at the end of the hallway, you'll see a doorway and you'll be able to remap. So there's this trend in the computational side to combine the mapping and planning, and to do the mapping partially. Inspired by this reasoning, recently there's been an increase in interest for more end-to-end learning-based approaches that go directly from pixels to actions. And that's one of the things that I wanted to emphasize here today. And a lot of these papers discuss or utilize this concept of going from pixels to action. So here is another paper. It's learning to explore using active neural SLAM. The architecture is here, but the main goal, as a matter of fact, I'm going to in the next slide, just black box this whole thing. Just put it into this gray box. There's a state and there's an action. And so this is structured as a reinforcement learning problem. Let's go back again. The state is the sensor pose reading and the observation, an image. And the action is the movement of the robot. And so it's roughly a reinforcement learning black box here. And the state, unlike classic reinforcement learning, the advent of deep learning has allowed us to use the robot's camera view, the image, as a state. And the action space is very low dimensional. You're just going to turn right, turn left, or go straight, just 3 actions. Okay. So it's a high dimensional state, 3 actions output. And this basic idea here is to, from pixels, give us the action. And this is the kind of thing that I think is really interesting in many methods of deep RL. The structure of the problem almost doesn't matter. You hope the structure is kind of learned in your network, but your input is pixels and your output is actions. And your knowledge of the system sometimes doesn't come to play. So in this learning to explore using active neural SLAM, they run their training, their RL agent that they're training, in an environment that I think is very interesting. Let me come back to this slide and talk about the environment for a moment. The paper uses this thing called Habitat. And see this link here, aihabitat.org. I recommend you watch their video. It's really interesting, but I have a couple of screenshots just to show you. If you watch the video, you'll see an agent going through a mapped out home. So in this screenshot, you see the robot has started here, the agent has started here, turned the corner, and is right there. And this is what it sees. What I like about the video, I just don't want to take the time to play it now, and you can see it on your own. But what I like about the video is this view changes as this little blue dot goes. Right? And then as the blue dot comes around down the hallway and around the corner and over here to where it can just see the kitchen, you see this view. Right? And of course, all the views in between. Habitat is a 3D environment that real photos have been stitched onto the 3D. So you have, it's a nice simulator because it's not computer graphics, it's actually the photos. And your state observation, the image that the robot would see if it were actually in the house, was pretty much spot on. It is the image that was collected and mapped to this 3D environment that then you can choose how to interact with that environment. So it's a really, really nice way to enable training of embodied agents, these virtual robots, in a highly efficient photorealistic 3D simulation. So going back here, we see that one of the tasks that this paper uses RL to do is an exploration task. You know, explore the whole apartment, make sure you get everywhere, right? And that's the goal. But this line I think is very interesting to emphasize. You can train the model in this thing called the Gibson domain and transfer it to the Matterport domain. These are different houses. Right? So the Gibson domain is one set of houses or apartments, and the Matterport domain is another. So you're not memorizing, the RL agent is not memorizing the particular apartment, but rather it's learning generalizable navigation skills that can then generalize to a different domain. Okay, the next paper, again, I'm giving sort of a brief tour of these papers just to highlight the main theme in navigation, which is moving away from classic navigation that gives full maps and also having systems that take pixels in, actions out. So where do we get lots of pixels, right? Where do we get lots of images of real world environments? The first thing that many of us think of is Street View. And these people from Google DeepMind also thought of that. So learning to navigate in cities without a map, instead of building an explicit map in an exploration phase, like is the classic approach, this paper uses end-to-end deep reinforcement learning for navigation, right? State of the art in large-scale real-world environments. And just as humans learn to navigate in a city without relying on maps, and this is a direct quote from the paper, it's their aim to show that a neural network agent can learn to traverse entire cities. Right? And in this paper, they use images and underlying connectivity from Google Street View, but they've repackaged it in a way that makes it very useful for researchers. They've repackaged it, taking a few domains, right? And all of the images are arranged in a graph. And so you can move your agent along this map represented by a graph and look around and get the Street View images. And so your state is readily available in this sort of simulated environment. Simulated, but it's also real world. And the agent has two inputs, the image and a goal description, you know, where it's going. And the action space is two things. One go left, right, left a little bit, right a little bit, and straight. Now, the same authors in their prior work of deep reinforcement learning used maze navigation. So in their prior work, they looked at complex maze environments. And this was popular in a couple of papers. The idea being it's a simple map, but it has some textures and you know it and you can build it however you want. And then you run your agent who doesn't know the map, right? The idea is that the agent only sees the camera view. So the agent in this paper is trying to take from pixels, camera view, and go to action. But the camera view is a view from this computer graphics simulated environment. Now, one might have thought that the path of research would have been to take these mazes and go more and more photorealistic by getting a better CG renderer and computer graphics model. But even with really good computer graphics, you're not going to get all of the complexities and the richness of a real world scene, including variations in weather and lighting and people and occlusions, et cetera, et cetera. So this work with the maps really allowed a jump in realism that I think is very useful. Let's see, is there anything else I wanted to say about that? This leaves open questions, right? These navigation algorithms involve building an explicit map during an exploration phase, and then planning and acting via that representation. As I mentioned before, and other papers have mentioned, this is the classic way to do it, right? But is that the only possibility? How do humans navigate? We don't typically memorize the map ahead of time and then take a walk in a new city, right? Maybe, if we have the time, maybe we do, and maybe that would be useful, but it's not realistic. We just go, and we learn as we go. And that's the idea behind using RL in these environments. And this is just some stats of, you can download this. This is freely available for research use. And it has, the graphs have between 7,000 and 65,000 nodes and about 3,600 images. Talked about that. And the goal, I'm not going to get into the details of how the goal is specified. There's a way to specify it relatively instead of absolutely, and it turns out that works much better in training. Now, this is the other thing that I wanted to mention. So the task that they evaluate their system with, one of them is a Courier Task. And you define the problem is to go to a set of random locations. And what they found is that using curriculum training works much better than not. And what curriculum training is give the goals, the goal locations that are close by first, and train the agent with those close by locations. And then gradually move the goal locations further out and continue to train the agent. And it turns out that this curriculum learning, which gradually increases the complexity of the learning task by presenting more and more difficult algorithms, it turns out that it kind of stabilizes and improves the training. And I think this has very interesting parallels to human learning. We see this concept of, if you understand how humans learn, perhaps you can use that insight to improve the training of the computational agent. It's not necessarily true that it would always work, but this is one of those interesting parallels to human learning. I'll go back here and talk a little bit about how, I'll just say briefly that these policies, right, this function pi in a reinforcement learning problem is the policy that takes state in and gives actions out. And these are represented by a particular type of neural network. It's a recurrent net called an LSTM. And it's popular in these type of problems, where you have a series of frames that you want to account for, a time series. This is a little bit more detailed about the goal navigation agent. Again, your deep learning standard things of several convolutional layers. And on top here, we have an LSTM. And this particular structure is sufficient to model the goal navigation agent. All right, now on the human navigation side, this is where I walk into literature that I have no business discussing because it's not my field. So you can stop me if I get things wrong. But the paper that I thought was interesting was Cognitive Maps to Cognitive Graphs in 2014. And one of the excerpts from the paper, imagine that you have arrived in a new city, You spent a few hours wandering around the downtown. Now back at your hotel, you need some coffee. You remember seeing a coffee shop midway through your wanderings, but instead of following your original route with all its twists and turns, you kind of have some idea because you have learned the network of streets that you can take a shorter path, and you do so. Right? So if this is true, then your knowledge of the network of streets can be characterized as a graph, and you're using it to navigate. So, you know, right away we see in this paper from, not from robotics and CV, but more on the human cognitive science side, you see the parallels, right? So there are some definitions. So routes in this paper are a series of place action associations. And I noticed that place action associations are like state action pairs in RL. There's a survey knowledge, which is a configural map-like knowledge of the environment location, including the metrics, distances, and directions between them. So this is what we would call in classic robotics, the environment map. And then a cognitive map, a globally consistent survey knowledge with a common coordinate system. And there's some, I guess this paper was addressing the controversy of whether we build up a cognitive map or that has a common coordinate system, or whether it's more like a relative graph. And so note the analogy with mapping and planning in papers in robotics and CV. So to briefly, you know, they talk about this graph. A labeled graph, though, has some information about the distances, but they might not be exact. And because they're not exact, you might not be able to get a really good estimate of that point to that point, for instance. But this point to this point, and maybe the fact that this point is a shortcut between from this point to this point, that can be obtained in a labeled graph. If you had this full survey, this would be more consistent with what the STEM side calls a map. And what they mean is that everything is in one common coordinate system and Euclidean distances can be found. So the aim of the study is to experimentally distinguish route graph, labeled graph knowledge using a virtual hedge maze environment. And this is one of those examples where the technology is helping the cognitive science researcher. So let me skip to this part. The human subject is wearing a virtual headset, and they see this, this kind of maze, right? And this is very reminiscent of the mazes that we saw the computational agent looking at. And what they did is they recorded the routes that the participants traveled as they learned the maze. So there's an exploration phase where the human is walking through this simulated environment. And then they analyzed whether they took direct paths or novel detours between learned locations. Right? So there's an exploration phase, and then test phase says, hey, why don't you go, like in the introduction, get coffee, and you sort of know where that might be, and they record what route you took. And what they found is that they were able to, let me see if I can show it here. First they do an exploration phase where they record everything. And then they say, oh, no, let's see. This one is an example of trial starting. So this one is going from the sink to the bookcase. This is all of the trials that a particular agent took. And then they ask, a human took, then they ask that person to go to the bookcase from the sink. And they notice that they take, this is one example where they take a route that they hadn't taken before, okay? And it's that kind of information that they use to make conclusions like the following. The findings of this experiment suggest that a labeled graph is the most appropriate level in the hierarchy to characterize the primary form of spatial knowledge used during active navigation, at least in a newly learned environment. So my takeaway from this one paper is that, one, it is an unresolved issue about exactly how humans use cognitive maps. And two, that the kind of research that's done in computational agents for navigation has direct parallels to that in human navigation research. So these papers are something that I presented in the socially cognizant robotics course, kind of giving students the background of the human side of the open issues on the human side and the open issues, both of these pretty state of the art on the robot vision side. So again, these discussion points, notice the issues of whether humans use maps or whether machine use maps are analogous. Notice the graph representation posed in the psychology literature paper is somewhat similar to that in the computer vision paper. And then the sidebar, that notice that the issues of learning, in this case curriculum learning, that are relevant to humans are also relevant to machines. So I think this has important implications too of systems where the human and robot works together to train the robot system. We want the humans training the robot, not the robots training the humans. Okay, so the final part of my talk is to look a little bit about the specific research in my lab. So I'm going to describe my PhD students' recent research. This is the work of Faith Johnson at hierarchical learning for steering angle prediction. Now, again, like curriculum learning, hierarchical RL has kind of good intuition in what all humans know. There's this concept of feudal learning where there is a manager and there's a worker. And there are goals and states, observations that the manager has, and there's goals and states and observations that the worker has. And what you want is an architecture that makes the overall performance of the network better by kind of simplifying the task of the worker and simplifying the task of the manager. But they kind of look at the problem at different scales, for instance. And our problem domain was what we call feudal steering, but the idea of steering angle prediction, right? And again, this is an example of from pixels to actions. We took a database of automated driving where you had both the dashboard images and the steering angle, the actual steering angle recorded. And there are several databases like this. And what we wanted to do was then pretend we don't have the next steering angle for the next time frame given the previous time frame. But just as a driver would decide on the steering angle mostly based on the image that the driver sees of the road, so too an RL system could do that, again, from pixels to action. And that's what we did. Here's the overall network. So there is a manager network and a worker network. I've expanded the worker network in this diagram. The manager network is somewhat similar. Multiple convolutional layers, and then an LSTM, and then a linear layer, and the output is the action. The worker sees the images in the past, not including the one the set immediately before, but in the a little bit displaced past, and it has the goal from the manager and its previous steering wheel, the steering angle, and it decides what the next steering angle should be. Now, the manager network produces this goal by doing something a little bit different. The characterization for the manager network it is also what subroutine am I working on? It has in it a classification of globally what it's doing. Do these images look like I'm turning left? Does it look like I'm bearing left? Does it look like I'm going straight? Does it look like I'm going in traffic? And what we did in order to visualize what was happening, we took some features in the network and put that raw data, but in feature space, into TS&E embedding space, and just kind of looked at what it corresponded to. Were we doing a good job with these features in delineating different traffic patterns, grouping, I should say, different traffic patterns. So it's kind of fun when you pull these dots in TS&E space and you look at the corresponding images that the feature data correspond to, you do in fact see this grouping. So as an example, I'm going to show the centroid frame, and then this row would be other dots around the centroid, as if I was clicking on a bunch of them to show the images. And you can look at the individual groups. So this is what one of the center frames of a cluster looks like. And here's some of the images of the neighboring dots. And you can see that this is a hard left, right? And this is another example. This is a left, but not quite as hard as this one. And this is another group. This is a going straight with a fair amount of traffic. So you're going straight and you're going slow. This is going straight and going fast, at least faster. This is a slight right, and this is a sharp right. So it's telling us that what we're learning is overall, what's the global action that's happening here, right? Before you spit out the exact angle, the exact steering angle, what is, does it help if you know if there's this higher level network that's saying, what is the macro action that you're taking? What is the traffic pattern that we're currently in? So this was the predicted versus real angle, matched very nicely. And we compared it to some other recent works, the MSE and the MAE, and we were able to get a significantly smaller error with ours, at least in some cases significantly. Okay, so when I think about hierarchical learning, which is an area that we're pursuing in my lab, there are a few things that I think about, and I think this audience would be great to have these thoughts for discussion. So can human in the loop work well with feudal learning? So in the feudal steering that I talked about, that both the manager network and the worker network were computational networks. But what happens if you have a human in the loop in a system where a human and a robot are working together? Can you pose them as input as a manager to the overall system? So does it work well with hierarchical learning? And what is the relation to imitation learning? Is imitation learning where the robot is learning from demonstration might be a little bit different than this human in the loop hierarchical learning. And in general, what lessons on hierarchical learning from cognitive science are useful here? So that's it. Thank you. Questions?
No questions yet? Well, I have one. This is a little bit out there, so forgive me if this is a little remote. So I work in sensory systems, often in really early sensory systems in the brain. Mm-hmm. And one of the emerging ideas as we look at what these sensory systems in the brain are actually doing and how they're changing as the animal learns about its world and learns what different sensory stimuli sort of mean, is that we see plasticity that we're increasingly thinking is not about improving your ability to detect the stimulus or discriminate it from similar stimuli, but instead improving the coupling between a stimulus and a behavior and giving that sort of relatively weak biological input from some neurons in the periphery of your body to actually be able to entrain 100 billion neurons to get them to do something appropriate. And as I was looking at your sort of from pixels to behavior, essentially mapping, I was feeling some hint of a synergy I haven't quite found yet about not just the transition from I see this, so I should take this behavior, but perhaps something more like I see this and it evokes a state, or it changes the motivation. It drives the manager network in some sense. I was wondering if you see any kind of way for those two ideas to jibe together.
Oh, I'd have to think about that more, but I do see the analogies. So this relationship between stimulus and behavior, if I think in RL reinforcement learning terms, it's setting up a policy,
right?
Where eventually it will use that stimulus to do that behavior. Yeah. Now, but you feel like it's a longer term thing as opposed to looking at the stimulus to deciding on the action right now. Your evidence is that it's
the evidence is sort of consistent with what you've described, that it leads to an action, but it's not necessarily a specific action. It's sort of context dependent, right? So based on that stimulus that predicts a threat, should I freeze, should I jump, should I hide, that kind of thing would be dependent on what it is. But the initial input seems to be sufficient, seems to be more guided towards driving the behavior than driving the actual sensory function, sensory discrimination or something like that. That makes sense?
Yeah, that's interesting. So I'd love to get a reference and read further about this.
Working on that.
Okay. So this is just your observation. These are your current observations.
These are ideas and sort of attempts to synergize a series of results that have kind of produced a story that isn't consistent with our initial framework, that sensory changes were related to sensory function. It seems more like sensory changes are becoming related to behavior. So upstream of the behavior rather than downstream of the behavior. So.
That's fascinating.
Anyways.
Yeah, that would be consistent and a very nice parallel.
Yeah.
Thank you.
Any other questions or comments?
Maybe I should put up the last slide.
Liz, are you popping in here?
Hi, I have a question.
Yes.
So I work on sensory motor control and sort of trying to come up with ways to model an artificial agent and understand the actions from more of a physiological perspective. And so I'm kind of curious because I hear the word action a lot throughout the talk, and conceptually it's different from what we identify as action, or from the standpoint of the physiology of the system. I guess it's because this is more of a space, a mental space, if you will, when this action is being described, because and then it's oversimplified.
This is this is something. I'd like to hear more about your question because I sort of, when I look at the literature, I see classic RL going from low dimensional state to an action space. And then deep learning kind of pushed the envelope to be able to handle a large scale state space, and in particular images, a high dimensional state space, in particular images. But a lot of the works I'm reading still have low dimensional action spaces. very simple left, right, forward kind of things. Now, granted, I'm right now, these papers were in the navigation domain, so it could just be an artifact of that. But what would you consider a more reasonable action space or set of actions?
Well, imagine that we have over 600 degrees of freedom in the body to control. And then there is the layer of the temporal dynamics of that, and the layer of intentionality and goal directness. So a whole bunch of that stuff is done in a goal directed with contact type of information to develop the dynamics. But then there's a whole other area that doesn't have contact information, in terms of the actual dynamics, developing the equations of motion, which are time dependent. So you have f of, x of t, x dot of t, and so on and so forth. So empirically, that doesn't cover it, because we have paths and trajectories that are independent, that exist independent of the temporal dynamics, and maintain the course of action independent of the speed or mass variation. So this is a different altogether question when there is a central nervous system cooperating with a peripheral nervous system and so forth to control the action. So it's just very different.
Right. And one of the things that, one of the lines of work that I didn't discuss at all, although it's related to a hierarchical RL, is the idea of learning what that community calls options. Has nothing to do with options in the financial world. Options or skills or macro actions all kind of mean the same thing there. And the idea is that you have your action can actually be a time series of actions. So for instance, it might be open the door, and as a macro action or an option or skill, using them to mean the same thing. But then open the door would have a series of actions that are environment dependent. So there's that. But I don't think that, when you talk about the 600 degrees of freedom for humans, although I suppose the control of robot humanoids, that literature has to work in a much higher
It does, but
action space.
It does, but one leaves out a lot of the cognitive issues, like take obstacle avoidance is totally a cognitive problem.
Yes.
And so it leaves that out. It's more the biomechanics, and then with the biomechanics, then you leave out the spontaneity of the action, which humans, and the stochastic component of it too. So it's, but yeah, I mean, definitely.
One of the trends that this is a little bit off topic, but I think it's interesting nonetheless. There's this tension between physics-based methods and learned methods, these data-driven methods, or even, it doesn't have to be physics, just structure of the problem methods. And one of the things that was shocking to me when I first read it is how well the deep learning Atari game playing agents could play their games without using anything about the rules of the game. And the analogy there with physics-based system is the learning to output these actions without using physics, but rather just using data. And frankly, I don't have, I'm not in one particular camp because sometimes the data-driven methods, so for instance, in these Atari games where the same type of training is used regardless of the game, and there's no understanding of the agent of the structure of the problem, nobody programmed in the rules of the game, and yet it can play it. the performance is undeniable, right? So you have, but then in some situations you can't get enough data for that kind of performance, where playing video games, you have the luxury of getting as much data as you want because it's a simulation. Anyway, I bring that up because of where does this use of dynamics go in the RL system, and where does the data-driven approaches go? And I imagine the future will hold some hybrid between the two.
So we will be meeting at, I think it's 3:30. So I'd love to also chat about, you mentioned during the talk, this emerging area of simulation and learning by watching the humans and so forth. So I'm interested in that too.
Okay,
Yeah.
great.
Thanks.
Fantastic, thank you.
I have one practical question. If students are interested in being involved in the NRT activities, or applicants that might be relevant or interested in some way, what's the process for getting involved?
And I should tell you that unlike a research grant, where, in a research grant, generally the students who are fully supported by the project are involved and that's it. This graduate program is open to all who want just a part of it, right? And then there's fellowships to apply for. So we call everybody NRT trainees, some of them being unfunded by the NRT, funded elsewhere, and some being funded by the NRT. But we encourage any student who is interested in being part of the community, which would entail going to the Chalk Talk series and just being a part of the community, to absolutely be part of the community. And then there's the applications. And we have a program coordinator. So I'll put the email in the chat. Socrates coordinator at rutgers.edu. Give me 1 second to just make sure I've got that right. Yes. Yeah, so students can send email requesting application info.
Okay, thanks. Unless there's any other questions?
Oh, we also have, robotics.rutgers.edu is the main Socrates page.
Okay, unless there are any other questions, I'll just say thank you very much, Kristen. This was a lot of fun.
Oh, I have
And,
one more question. Sarah, can we see your baby? Oh, hello.
There she is. She's been a frequent visitor in a lot of my meetings these days. Pushing science to the new frontier.
Oh, yes. You have a lot to say. We're very interested.
She does.
Okay.
Yeah, it's so good to see you, and thank you so much.
Thank you. Thank you, everybody.
Thank you, Christine.
Thank you, Christine. I'll see you in 20 minutes or so, right?